uh, in this video we'll try to solve a problem on thick cylinders. Okay, so in the last video we derived the Leng's equation, right? The Leng's equation, normally the final equation, it will comes here, that is P at x equal to b by x square minus a. This is one equation. And sigma c, circumferential stress at x equal at a value of x, is b by x square plus a. These two equations we derived in the Leng's equation in the last video. Here we just check it here, where the x is at a particular distance of the wall thickness. Suppose this is where the inner radius and this is the outer radius. In between that, anywhere x, okay, x at a from the center, that value at that distance, what will be the circumferential stress and what will be the pressure at that point here. Okay, where a and b are the constants, we have to apply the boundary conditions and try to find out the values of a and b. Then if we substitute, then we'll get the pressure at particular points and circumferential stress at a particular point. This is what we derived in the last video. Now we'll solve the problem on base on the Leng's equation here. Okay, same equation. First I'll try to read the problem, then we'll write the data here. A thick walled cylinder, it is a thick walled cylinder, cylindrical pressure vessel, has inner diameter, is given inner radius of 150 mm. We'll try to write the data here. The thick walled, the cylindrical vessel has the inner radius. Inner radius is, that is, I will write Ri equal to 150 mm. This is the inner radius. And outer radius, he is given outer radius of 185 mm. This is 150 and outer radius is 185 mm. Draw a sketch. You have to draw a sketch showing radial pressure and hoop stress distribution. You have to calculate the radial pressures and you have to calculate the hoop stresses. Hoop stresses means the circumferential stress, right? Both are same. You have to calculate and you have to draw the sketch. You have to draw these stresses distribution in the section of the cylinder, in the section of the cylindrical wall. When an internal pressure of 10 meganewton per mm square, he is given the internal pressure, that is Pi. At Pi, internal pressure equal to 10 meganewton per meter square. Convert the Newton per mm square. This will be equal to 10 into 10 to the power of 6 divided by 10 to the power of 6 Newton per mm square, right? Newton per mm square. This will be equal to 10 Newton per mm square or MPa. Both are same, megapascal and Newton per. I will write this one as MPa, or both are same. That will be equal to 10 Newton per mm square. Both are same. Okay. So this is Pi. He is given. You have to draw the sketch here. So how we start that? This data they are given. Just I'll keep it in this. The problem I'll remove here because all the data are be copied here. Okay. First we will draw the thick cylinder. That is, just I'll draw here. This is inner radius. Here this is the point and this is the outer radius. Okay, and this is the center point. Okay, this is the center point. This is the center here. Okay, so first Ri, this is inner radius. Okay, just I'll note down here, this is inner radius. This will be Ri equal to 150. That will be, I can write it as x equal to 150, right? Because we are particularly dealing with the Leng's equation x equal to 150. This is x equal to 150 or Ri equal to 150. Now R naught, this is R naught equal to how much? 185. All are in mm, just I'll write 185. That will be x equal to, that will be equal to x, right? At x equal to 185, x equal to 185. Next, what is given? Pressure at I. It means it is inner. When x equal to 150, it is inner radius I. He is given 10 MPa. So here I'll write here inside here this pi somewhere we'll distribute later here. Okay, this is the data is given. Now first we will write the Length's equation. Length's equation p at x equal to b by x square minus a. This is one equation, Length's equation. Second one, sigma c at x equal to b by x square plus a. This is one equation. Now based on the data given and apply the boundary condition and try to solve the constants a and b from these two equations. Okay, so now this I will call it as a and this I will call it as b equation. Okay, boundary conditions. Okay, when ri means when x equal to 150, I'll write when x equal to 150 mm at a distance x equal to 150, and what is the pressure here? That is pi equal to 10 Newton per mm square. That is px. That is px equal to px equal to p of how much? P of 150. P of 150 equal to how much is given? Pressure at 150 mm is given inner pressure, that is 10 MPa. 10 MPa. This is one boundary condition. Okay. When x equal to 185, what is given? Something is given. When x equal to 185, that is R naught. X equal to 150, that is R naught. That will be equal to R naught. This will be equal to Ri, right? This will be Ri. What is the value here? P equal to 0 here, because he's P. The pressure, it is at 0. It is outside pressure, it is 0. He is not given. That is P naught, Px equal to P naught, P0, P outside, it will be equal to 0. If pressure equal to 0 at the outside of the outer wall, then it is there is no stresses here. There is no stress distribution. Therefore, that will be equal to sigma c naught. Circumferential stress at the outside, it is 0 because pressure at the outside, it is 0. Now first we will try to sketch the pressure distribution here. P first in the inner wall, P how much is there? P of x equal to P of 150 equal to 10 MPa. Always the pressure distribution draw the downside and circumferential stress distribution draw outside, draw the upper part here. Okay, now I am first drawing the pressure distribution on the on the downside here. At x equal to 150, how much is the pressure here? 10 MPa. Just from here to here, just mark 10 MPa. From here to here, mark 10 MPa. And this is P. This is P I equal to P at 150 equal to how much? This is the 10 MPa. 10 MPa. Okay. And outside, how much is the pressure? Pressure is 0. So this is the 0. This is the 0 value. So here P naught equal to how much? Sigma C naught. If pressure is 0 at outside, circumferential stress also 0. Now join, this is 0, this is 10 here. Now this is the from here to here, join it here. Okay. This is the pressure distribution of the wall along like this. It means at the inner wall it is maximum 10 MPa, at the outer wall it is 0. Now come to the next point. Apply these boundary conditions. Come to the problem now. Apply this boundary condition and try to solve A and B. Okay. Now I am solving that. Apply first when x equal to 150, that is P of 150. P of 150 is how much is there? That is 10 MPa. 10 equal to B by x is how much? 150. X is 150 mm. That is 150 equal minus A. This is one equation. Okay. Come to the second. Okay. When sigma c at x equal to 185, right? Sigma c at x equal to 185 equal to B by X is how much? 185. 185. X is 185. This is 180. When x equal to 180, this is 180, right? This is 180 outside R0. This is 150 inner radius. When x equal to 180, that is R0 equal to b divided by x is how much? 180. Here substitute 180 plus a. 180 square and this 150 square. Okay. Now call it as this one equation 1 and equation 2. Now solve a 1 and 2. You know the simplification. Just I'll go like that. It means you can make it plus here on both sides. These two cancels. B will come into picture. After that, the b value, substitute any one equation. We'll get the a value here. Okay. This just do it here. Simplify. Solve equation 1 and 2. 1 and 2. From that, we will get first b value. B equal to, after solving, we will get the b equal to 656769. 656769.7. This is b we will get here. Okay. Now substitute b value in any one equation, either 1 or 2 here. So you can calculate the a. Okay. After substituting, we will get a value, the constant a equal to 19.2. 19.2 here. Okay. Now we found the a and b value. A and b value. Now what are the upper side is the stress distribution. We have to sketch the stress distribution. Now already we sketched the pressure distribution. Now upper side it is the circumferential stress distribution. For circumferential stress distribution, we have to take which of the equation here? The second one. Second one, right? In the second equation, first put x equal to 150. The distance is 150 millimeter. And substitute this is 150 millimeter, substitute b value and substitute a value. Okay, you will get the circumferential stress at x equal to 150. That value you have to copy here. Okay. Similarly, when x equal to 185, when I substitute x equal to 185 millimeter outer radius, the b you know, a you know, and in here 185 distance. Substitute and you will get the circumferential stress at the one at a distance of 185. That you have to the value you have to copy here. We will do that one here. Okay, just use b from equation b. Equation b, when x equal to 150, the radial inner x equal to 150, then sigma c x equal to sigma c of 150 equal to how much? At sigma c, circumferential stress at 150 mm, how much we have to calculate. So now we have to, I am calculating here sigma c, therefore sigma c of 150, that will be equal to ri, both are same, that will be equal to sigma ri, right? Sigma ri equal to how much? Both are same. That will be equal, just I'll write here, that will be equal to sigma ri equal to substitute b value, that is b by x square plus a, first substitute. This will be equal to b is how much? 656769.7 divided by x is 150 millimeter. X is 150 square plus a is how much? 19.2. 19.2 here. Okay. Now calculate the right side value here. You will get, therefore after calculation you will get here the 48.4 MPa. This will be sigma c at 150 equal to sigma at 150 equal to 48.4 MPa. This is circumferential stress at a distance of 150 millimeter. That will be equal to sigma ci, both are same. That will be equal to sigma at ri. Both are same. Sigma c at ri. Sigma c, just copy here ri. This is better. Okay. Here also sigma c, circumferential stress at ri. Now at 150 mm, find out how much is the circumferential stress? 48.4 4. Now I am drawing here 48.4. From here to here, this is sigma C I equal to 48.4 MPa. This is the value of the inner wall. Now calculate the outside, at the outside wall here. Same again apply here, apply the same and apply the boundary condition here. Okay. When x equal to how much? X equal to 185. From equation B, when x equal to 185, how much? Sigma C equal to 185 equal to sigma C at the R0 at outside equal to B by 185 square plus A. Okay, you know that B value, substitute that 656769.7 divided by 185 square plus A is how much? 19.2. Calculate here. So you will get, after simplifying, you will get that the 38.4 value, that is 4 MPa. This is sigma C at 185, that will be equal to sigma C at R0. This is 1. Now how will mark at the outside of the wall here at radius 185, at radius 185 mark 38.4. This is 48.4 and here this you will get here the 38.4. Just from here to here, that is sigma C naught equal to 38.4 MPa. Now this is the outside value. Now join here and here, that you will get here this is the circumferential stress distribution. Okay, this is how the pressure distribution downside and circumferential stress distribution upper side here. If you see here, inner wall circumferential stress is maximum 48.4 MPa and pressure also maximum it is 10 MPa. If you see the outside, the pressure, circumferential stress is 38.4 MPa and pressure is 0. Pressure at outside is 0 here. So from this, whatever the stress developed is inner wall is more. The pressure, and because of the fluid you are placing inside, the pressure and the circumferential stress, it is more in the inner wall of the cylinder. As it goes onto the thickness, as the x will be increases, its stress and its pressure value goes on decreases, and finally here you will get sometimes the 0 and the circumferential stress also it will be less here. Okay, this is how the pressure distribution along the thickness. This is the thickness, right? That you should understood here. It means finally you come to know that in the inner wall it is more stress distribution and the pressure. Outside it will goes on decreases here. Okay.